Hello, students and fellow tabletop wargamers. This lesson will be about combinatorics, a discussion of combinations and permutations, and I will go over what they are later. But the first thing we need to learn is the concept of the factorial, which is a discrete concept, because the nature of combinations and permutations are for counting, specifically counting different arrangements or different ways to choose things. So how to calculate a factorial is that it's denoted by a number in front of an exclamation point. And you multiply the number times the next integer lower, times the next integer lower, times the next integer lower, all the way down to 1. So 5 factorial here is 5 times 4 times 3 times 2 times 1. And when you calculate it out, it's 120. Do note that this might be a little confusing, but 0 factorial is equal to 1. 1 factorial is equal to 1 because it's just 1 times 1. But there is a thing called 0 factorial, and it is also equal to 1. Even though there's no integer less than 0, there's only one set with this possibility, and so 0 factorial is 1. And why this is important is you'll see in some of the examples later that 0 factorial does come up. So now we'll discuss the difference between permutations and combinations, and it might be a little confusing. You might not understand it at first, but by the end of the video, I guarantee that you'll have a good idea of when to use the permutation and when to use the combination. So you can think of permutation as placing. It starts with a P, placing starts with a P too. So you use this formula to calculate the number of ways to arrange objects where the order matters. And the combination, you could think of it as choosing, right? Combination starts with a C, choosing starts with a C. It's easy to remember this way. The number of ways to arrange objects regardless of order. So when you have, for example, a set of people and they're competing in a tournament and there's first place, second place, third place, the order matters. So permutations are important. But if you're going to choose a random set of 3 winners out of, say, 25 who are going to win exactly the same thing, a $10 gift card, then you will use combination. So how to calculate permutations is you have the N and you have an R. So N is the set that you're choosing out of or placing out of. And R is how many places there are. So for example, if there are 25 contestants and there's first place, second place, third place. Now there are 3 places and 25 contestants. So N would be 25 and R would be 3. And so this would be 25 factorial divided by N minus R, which is 25 minus 3, or 22 factorial. Now, if you have 25 contestants and you're choosing 3 of them to win the exact same gift card where order does not matter, then you have 25 factorial divided by 3 factorial times 25 minus 3, or 22 factorial. So let's go to some example problems here. How many ways are there to place 3 people at a bar with 3 seats? So the important thing to note here is that a bar is generally straight. And so since each seat is different, now we have an order. We use permutations. So you do 3, NPR 3, and NPR is just shorthand for permutation. And when you put this into the formula, you get 3 factorial divided by 3 minus 3 factorial, which is 0. Remember what I said? 0 factorial is important. You get 3 times 2 times 1, which is 6, divided by 0 factorial, which is 1. You have 6. When you write out all the different combinations, well, the different permutations of placing 3 people at a bar, you see that there are 6 ways to do this. So, how many ways are there to place 3 people around a round table? So, you might be thinking, order doesn't matter, right? It's a round table. Well, I'm going to tell you that order does matter. Why? Because even though some of the combinations or the different arrangements, let's say, are the same, order does matter because of the placement of an individual in relation to another individual. So who sits next to who? So now we have 3 NPR3 divided by 3, and that's 2 different arrangements to seat 3 people in 3 seats around a round table. So how do we get to this? Well, there are 3 ways to rotate each configuration. So you divide by 3 since it's a round table. What I mean is ABC, BCA, CAB are all the same because it's a round table. And so you have ABC, ACB, BAC, but BAC is the same as ACB. You got BCA, and that's the same as ABC. You have CAB, that's the same as ABC. And you got CBA, which is the same as ACB. So when you list it all out, you can see that there are only 2 ways to place 3 people in 3 seats around the round table. And you use a permutation, not a combination, because, for example, let's look at player B. He can have player C on his right and player A on his left. Or he can have player C on the left and player A on the right. So even though it's a round table and you might not think that order matters, order does matter because of who sits next to who relative to who. And when you look at the combination formula, why is the answer not 3 NCR3? Well, let's calculate this out and see what it is. It's 3 factorial divided by 3 factorial times 0 factorial, which is equal to 1. Now let's think about what question NCR is trying to answer. In this consideration, it does not matter who is sitting relative to whom. All that matters is that the people are seated. So the meaning of 3 NCR3 is you are choosing a subset of 3 people to fill 3 seats out of a set of 3 people. And there is only one set of 3 people who can fill the seats. Why? Because there are only 3 people, you're choosing 3 of them. There's only one way to choose 3 people out of 3 people. So that is what the choose or the combination answers. So now let's get to the next slide. In this slide, we're going to have a Warhammer 40K example. And this is going to show a little bit of the amount of options that you have when you're list building. So currently, as of March 2025, there are 9 different Questoris Knights, 2 different Dominus Knights, and 4 different Cerastus Knights in the index. And the index is like a catalog for those who don't play Warhammer 40K. And so, let's say you own 4 different Questoris Knights, 3 different Cerastus Knights, and you want to build a list with 2 Knights. How many ways are there to build a list? Here, since a list means a team, there's no place 1 or place 2. You're just simply selecting a subset of 2 knights out of 7 knights. You do 7 NCR2, which equals to 7 factorial divided by 2 factorial times 7 minus 2 factorial. And that gives you 7 factorial divided by 2 factorial times 5 factorial. And to do the math easily, remember what the factorial means. It's 7 times 6 times 5 times 4 times 3 times 2 times 1. What is 5 factorial? 5 times 4 times 3 times 2 times 1. So, since your numerator has 5 factorial included in the 7 factorial, you can essentially cross them out of the numerator and the denominator. And in the numerator now, you have 7 times 6. And in the denominator, you have 2 factorial, which is just 2, because it's 2 times 1. So you have 6 times 7, which is what? 42 divided by 2 is 21. So if you own 7 knights and you're trying to run a list with 2 knights, you have 21 different ways to do it. And for Warhammer 40K players, this is not including any of the other agents or whatever else is going to fill your list. This is simply how many arrangements of bigger knights you can have. So now, in the next example, you own 4 Questoris Knights and 3 Cerastus Knights, just like before, and you want to build a list with 3 Knights. But here are some restrictions. You want to take 2 Questoris Knights and 1 Cerastus Knight. How many ways are there? So remember from lesson 1 that the keyword and means multiply. The keyword or means add. So, first of all, you want 2 Questoris Knights and you have 4 of them. So you have 4 choose 2. And you're trying to choose 1 Cerastus Knight out of 3. And that's 3 choose 1. And do note that if you're choosing 1 Cerastus Knight out of 3 Cerastus Knights, that's 3 possibilities you can have. 3 choose 1 comes out to 3. Anything choose 1 comes out to itself. And since you have the and keyword here, you multiply both of the arrangement quantities to get the final quantity. So when you do the calculations, you come out with 6 times 3, and that's 18 different options. So now we have our final example using the 4 Questoris Knights and 3 Cerastus Knights. You want to build a list with 3 Knights, but there's a different restriction now. You want 2 Questoris Knights and 1 Cerastus Knight, or 1 Questoris Knight and 2 Cerastus Knights. So, meaning that as long as you're not taking 3 Questoris Knights or 3 Cerastus Knights, you're okay with any option. How many ways are there to build this list? So now we have a few different things we have to consider. So here we have the or keyword. That means you have to add it. So what we're going to do is we're going to take 2 Questoris Knights and 1 Cerasus Knight separately as one scenario. Then we're going to add the number of combinations that we can get from the other scenario, which is 1 Questoris Knight and 2 Cerasus Knight. So when you look right here, you have 4 choose 2, meaning you're choosing 2 Questoris out of 4 Questoris, multiplied by 3 choose 1. You're choosing 1 Cerastus out of 3 Cerastus. Then you have a plus here. You're adding the number of combinations from the other scenario, which is choosing 1 Questoris out of 4 and 2 Cerastus out of 3. So remember from the previous scenario that choosing 2 Questoris and 1 Cerastus gives you 18 different options. So we're just gonna put 18 here, and we're gonna add the new set of options that comes from 1 Questoris and 2 Cerastus. And how you get that is 4 choose 1 times 3 choose 2. And when you calculate it all out, you get 18 plus 4 times 3, and that's equal to 30 different options. So now we're gonna discuss a topic that's often mentioned in the Imperial Knights community. A lot of people say, we don't have enough data sheets. We need more data sheets. We need more variety. We need more choices of units we can take. And in these next 2 examples, I'll show you that with a set of 15 knights, there are very many different options that you can have for list building. So in a list, it's generally accepted that you can bring 1 knight, 2 knights, or 3 knights. How many options are there if each knight can only be taken once? Meaning, let's go up here. You can't have 2 paladins, or you can't bring 3 errants. You can only have 1 of each type, and you can bring either 1 or 2 or 3. So remember what I said about the or keyword. When you have the or keyword, you're adding. So out of a set of 15 knights, you can bring 1 knight, so that's 15 NCR 1, because you're choosing 1 knight out of a set of 15, or 2 knights, so we're adding 15 NCR 2, you're choosing 2 knights out of 15, or you can have 3 knights, and we're adding 15 NCR 3. And when you do the calculations, you have 575 ways to build a list. And that's with the restriction that each knight can only be taken once. Now, in game, that's not true. You can bring 3 of the big knights if you want, and they can all be the same. So, how many options are there if multiples of any knight can be taken? Given you can bring 1 knight, 2 knights, or 3 knights. So, for this final question, we're going to break it down a little bit. Now, there's a different way to do it that I have below. You can kind of see it in the slide here. But let's do it the way we've been doing and just break this out. So, you can either take 1 knight. It doesn't matter if multiples of any knight can be taken because you're only bringing 1 knight. So, here we have 15 NCR 1, just like in the previous example. And then, the next choice you have is bringing 2 knights. you can either bring 2 different nights, or you can take 2 copies of one night. So here we got taking 2 copies of one night. Well, if you're taking 2 copies of one night, there's 15 night types to choose from. So essentially, it is as if you're choosing one night. You're just taking doubles of it. But it comes out to the same, 15 NCR1, because you're choosing one night type out of 15 night types. Okay, next, we could take 2 different nights. So now what we're doing is, out of a set of 15 different nights, we're selecting 2. So that's 15 NCR2. Does that make sense? Now, those are the only ways you could take 2 nights. 2 of the same ones or 2 different ones. And we covered that. So now we get to the 3 nights. The simplest scenario is you take 3 of one night. There's 15 nights, and you're choosing one night to take a triple of. So, just as before, it's 15 NCR1. Now, you could take 2 of one night and 1 of another night. That's another option. So here, what we're doing is we're selecting one night that we're going to take 2 of, right? So the way I modeled it is 15 NCR1. You're choosing one night to take a double of, right? And now we have to take 1 of another night. So if we're taking 1 of another night, since you've already selected 1 and this other night's different, we have 14 options to choose from. And since you're selecting 1, that would be 14 NCR1, or I just put 14 here. And finally, you could take 3 different nights, and that's pretty simple. 15 NCR3. And when you calculate all this out using the formula that I had before, you have 815 options. If you can take multiples of any night, there is a set of 15 nights you can choose from, and you can either take 1, 2, or 3 nights. You have 815 ways to build that list. And that's not including allies. So, what I'm going to say here is we have a lot of different options for list building, even with just 15 data sheets for the bigger nights. And now, back to the more mathematical side of it. Here's a formula for combinations with replacement. Wow, how convenient, right? Well, here, the formula is a little bit different from the original choose formula. This one is n plus r minus 1 factorial divided by r factorial times n minus 1 factorial. And when we look at the previous example, we just have to break it down into bringing 1 night, bringing 2 nights, or bringing 3 nights. And you put it into this formula. So it would be 15 as n, 1 as r, which would be 15 plus 1 minus 1, which is 15 factorial, divided by r factorial, which is 1, and n minus 1 factorial, which is 15 minus 1, or 14 factorial. So we got 15 factorial divided by 14 factorial. You cross out everything from 1 to 14, you got 15 different options for taking one night with replacements. Remember what I said? That when you're choosing one night, the replacement part doesn't matter? Well, it happens that it's the same. It's 15 here. So now we go on to the 2 nights. You got 15 options, and you have to select 2 nights with replacements. And what with replacements means is you pull one night out of the stack, and then you put it back, and then you pull another night. So essentially what that means is you can take doubles of it, right? So now n is 15 and r is 2. And you get 15 plus 2 minus 1 factorial divided by 2 factorial plus 15 minus 1, which is 14 factorial. And when you do the math, you get 120 options. And lastly, you can bring a list with 3 knights with replacements, meaning you could take triples, you could take doubles, you could take singles. How many options are there? So we do the same thing. We plug in 15 for N, 3 for R, and what you get is 680 options. And when you add 680 to 120, what do you get? 800, and then you add 15, you get 815, just like how we did it a different way before. And in order to finish this video, we'll give you our last formula, which is the formula for permutations with replacement. Now, this previous formula is combinations with replacement. And remember, combinations are for choosing with no particular order mattering, right? You're just choosing knights. You're not placing knights, you're choosing knights. So that's why we use the formula for combinations with the replacement. But now we got the formula for permutations with replacement, which is a lot simpler than this crazy factorials and multiplying and dividing and adding and subtracting. So the formula for permutations with replacement is simply n to the power of r. So what would be a scenario in real life where we would use permutations with replacement? Well, one thing could be a schedule for which an employee can be scheduled twice. It uses permutations because a schedule is ordered. A schedule has a slot for 10 a.m., 11 a.m., 12 a.m., 1 p.m., for example, and so on. And let's say you have a set of 15 employees that you can put into these time slots. And some employees are willing to be scheduled multiple times. So they want to take a double shift, for example, or a triple shift. You could use formula for permutations with replacement in this scenario. So anyway, for all you math students out there, I hope that you learned something, and I hope this video will become useful to you and have some application at school and outside of school. And for the wargamers out there, I hope that this video kind of gave you some insight on how many actual list options there are, given a relatively small choice of data sheets, 15 data sheets for the bigger knights that we can choose from. You can still get 815 options. Given some of the knights are not so good in certain detachments, you can always put restrictions on it, and you can see from the previous examples that even with restrictions, you do have a lot more than a handful of options. So that being said, thank you all for watching this video, and if you liked it, if you learned something, then hit the like and subscribe. That way it'll help my channel. And if you have any questions or any comments, then please feel free to drop a comment down in the comment section. And if anybody wants lessons or tutoring, I may be available. At the time of making this video, I am available, but I don't know what my schedule will be in the future. But feel free to send me a message or comment with a request for tutoring. Anyway, have a great day and pass your next exam.